Great to have you back. And before we get into the laws of thermodynamics, let us do some preparation for it. So in this lesson, we'll cover 1. What are PV diagrams? 2. What is the work done by a system? 3. What is heat in or out of the system? And 4. What is the internal energy of a system? Well, we'll also cover various kinds of thermodynamic processes. Before we go ahead, let me request you to press the subscribe button if you've not done already, so that you continue to get notification on all videos that are released. And if you like it, please give it a thumbs up and do share with someone who can benefit from it. So as prep work, let us take a look at various ways how energy of a system can change. To study this, we will assume that our system is an ideal gas which is put in a cylinder with a piston that can move up and down. Well, let's also put some sand on top of the piston so that the upward pressure due to the gas is equal to the weight of the sand, and so at any given point of time the pressure of the gas can be considered equal to the weight of the sand on the piston. We will also assume that the walls of the cylinder are insulating and therefore do not allow any transfer of energy as heat, and we will place the cylinder on a thermal reservoir that provides constant thermal energy when desired to the system or the gas. So I'll be using the word system and gas interchangeably throughout the chapter because gas is the system in this setup. Let me also quickly tell you what an ideal gas is. So it is a gas whose molecules occupy negligible volume, do not interact with one another, or there is in a way no intermolecular force, and if they collide, the collision is perfectly elastic and there is no loss of kinetic energy. Now, this reservoir that is providing the heat could be a hot plate with a control knob that can be turned up or down depending on the amount of heat to be provided to the system to, well, either increase the temperature of the gas or maintain the temperature of the gas. So let us say at this point of time the pressure of the gas is P and the volume is V. Then the same information of P and V can be plotted on a PV graph, and let us say it falls here. Well, physicists call this the state of the gas. So if we change its pressure to P1 and volume V1, then it could be here, or if the pressure is P2 and volume V2, it could be here. So you can see any point on this PV plane can represent a state of the gas. And you might ask, why should T or the temperature not be a dimension? Maybe on the z-axis? Well, we do not put T on another axis because it gets fixed by the P and V values and is not another independent variable. So let's say the system or the gas is at an initial state I such that its pressure is Pi, volume Vi, and we take it to a final state Pf and Vf. Well, this can be done in various ways. One way is that the gas can push the piston up so that the new volume becomes Vf and pressure Pf. Then this simple process is called a thermodynamic process, and there could be, well, many more variants of this thermodynamic process that can be adopted to achieve the same results. So during any thermodynamic process, two things can happen. One, heat can be transferred into the system or the gas from a thermal reservoir, and when heat is transferred into the system, we learned in the earlier lesson, it is called positive heat, or it can be taken out of the system, in which case it is termed negative heat. Two, the other thing that can happen is that the gas can do work if it raises the piston and the volume expands in the process. This is termed as positive work since the gas molecules are actually pushing the piston up by constantly hitting it and therefore doing real work, and therefore this is termed positive work. Well, if the piston pushes the gas down, then we can say it's the opposite, or the gas is doing negative work. Note that we are not talking about the work done by the piston, even though the piston has done positive work. We are interpreting it as the gas doing negative work. So in summary, when the volume of the gas gets compressed, we say the gas is doing negative work, and when it expands, we say gas does positive work. So another very important assumption in any thermodynamic process is that all changes occur very slowly so that the system is in equilibrium at all times. And to emphasize this point, let us study it a little deeper. So instead of sand, let us take a few large weights on top of the piston, and if you were to suddenly remove one weight to reduce the pressure, what do you think would happen? So imagine you are doing so, and what you will see is that the piston shoots up rapidly, and therefore the pressure of the gas also changes suddenly, and in this short time the pressure on top may be lower than the pressure at the bottom, and the pressure of the gas as a system will not really be defined, since various parts of the gas within the cylinder would be at different pressures. So you can say the state of the gas during this time cannot be plotted on this PV graph because we do not have a clear PV value to plot. In a way, the state of the gas during this time will be what you can say as off the charts. So that is the reason we use sand here, or maybe very small pellets, so that if we wish to reduce the pressure of the gas, we can do so by reducing the weight on top by, let's say, removing a few grains of sand at a time, and by doing so we make very small changes in the system and do not disturb the system's equilibrium. And you can also note that this is a reversible process, so you can put the grains back and the piston goes down again and restores the volume and pressure. So you can go down and then up again on this graph. Now let's go ahead and calculate what is the work done by a gas in a thermodynamic process where the gas expands and pushes the piston up, thereby doing positive work. So to find this, we remove a few grains of sand from top of the piston and therefore allow the gas to push the piston up by a very small distance ds. Since the displacement is very small, we assume that the pressure has not changed much, and say the pressure is P during this movement ds. So we assume that it does not really change because the distance covered is very small. So if the pressure is P during this movement ds, then the force exerted by the gas is nothing but F is equal to pressure into the cross-sectional area of this cylinder, and therefore the delta work done by the gas dW is equal to force into displacement, which therefore is equal to P into A into ds. But we know that the product of cross-sectional area A into the distance ds is equal to delta volume. So we can write this as dW is equal to PdV. Well, if we keep removing the grains of sand incrementally, the piston will keep moving up and the volume will eventually change from Vi to Vf. Then we can integrate both sides to find the total work done by the gas, or W is equal to integral of PdV while it pushes the piston from the initial position to the final position. Now, what we need to remember here is that during volume change, the pressure and temperature also changes. So we really need to know how P changes with volume to do this integration. Well, if pressure is a constant, then this integral is very simple and it will simply be P into Vf minus Vi, or V final, volume final minus the initial volume. So let us discuss a few parts where we take the gas from initial position I to final position F. So the most common path you will see in physics textbooks is this, where the volume is allowed to expand by removing grains of sand slowly. So this is the initial starting point when the gas is at pressure Pi and volume Vi, and when we remove a few grains of sand, the volume increases and the pressure reduces, and then we again remove a few grains and the volume further increases and the pressure further reduces. We keep doing this till we reach V final and P final. So the area under this graph then gives the work done by the gas, and just to show that indeed the area under the graph is the work done, consider this change of state of gas between this point and this point where the volume changes by dV. Then since the change is very small, we assume that the pressure has not changed much, and let us say it is pressure P. Then the work done is P dV as we derived earlier. Well, we can take another dV increase in volume. Say now the pressure is P dash, then again the work done is P dash dV. And we can keep making such boxes left and right such that the area of all boxes put together is the work done by the gas. So this calculation or summation of these boxes can be done very conveniently using integral calculus, such that the integral of P dV between Vf or volume final minus volume initial, that is Vi, gives the exact area under the curve. So as a summary, what you need to remember is that the area under the curve gives the work done by the gas, and since the gas is expanding or volume is increasing, this work is considered positive. So by this logic, if the gas had actually moved from this position to this, then the volume would have contracted, and while the area under the curve is still the same, the work done should be considered negative. So as a thumb rule, any movement in the state of the gas on this PV diagram to the right is positive work done, and any movement to the left is negative work. Well, another path could be that we take the gas first from I to A and then to F. So what we do is first we increase the volume of the gas while keeping the pressure constant. That is, we do not remove any grains of sand between I and A. But then you may ask the question, how do we make the volume change? Well, we can make the volume change by adding heat and making the kinetic energy of molecules of gas higher so that they start bouncing around faster and harder against the piston head and therefore push the piston up. Now, to add heat, we make use of the heat reservoir, where we slowly increase the temperature to some value TA, and when we do so, the gas expands and pushes the piston up. That means the system is doing positive work. Also, we can see that heat is being added to the system, so it will be considered positive. Now, once the gas reaches state A, we reduce the pressure but keep the volume constant. Now, to keep volume constant, we clamp the piston so that it cannot move up and down. So now to reduce pressure, the only way is to reduce the kinetic energy of the molecules so that they hit piston less hard and less often, thereby reducing the pressure inside. Well, we therefore need to cool the gas by reducing the temperature of the reservoir slowly to some temperature TB, and in the process the gas loses heat to the reservoir, and therefore we say negative heat is added to the system or the gas. Well, for the overall process, you can see that the work is done during step IA only and is represented by area under the curve. You can also see no work is done during step AF since there is no change in volume. Remember, work, positive or negative, happens only when the volume changes. Well, you could also go from I to F taking this route where we first keep volume constant and reduce the pressure, and then we keep pressure constant and increase the volume. And you can see that the work done here is less than both the previous paths. You may like to try and figure out what happened in each of the two steps, as in if the work was done or heat was added or taken out. Now we can even take a very longish path like this and make the gas do a lot of work, or take this path and make the gas do very little work. So you'd have probably figured out that there could be many more paths to reach from I to F. In fact, there are infinite number of paths where varying degrees of work W is done and varying values of heat put in the system or taken out. So we can therefore say that the heat put and work done depends on the path we take from I to F. So all that we have learned so far equips us to understand the first law of thermodynamics. So you saw that when you take the gas from state A to state B, W and Q can be different depending on how you take the gas from A to B. If it is this process or this or this. Well, what scientists found was that while W and Q can vary, but surprisingly, the quantity Q minus W remains the same for all processes. That is, if you calculate Q minus W for this process or this, the difference Q minus W remains the same as long as the initial and the final state is the same. So if the quantity Q minus W is always the same, irrespective of the path taken, it must be some intrinsic property of the system, or in simpler language, naturally belonging to the gas, and that is what we term the internal energy of the system, and we write the change in internal energy as E internal final minus E internal initial, or delta E is equal to Q minus W. And this is what we call the first law of thermodynamics. And if the system undergoes very small change, we can write it as dE is equal to dQ minus dW. So the internal energy of a system increases if we add heat to the system and reduces if the system does positive work by pushing the piston up. So here's one rule for you. In earlier chapters, we've always talked about work done on a system, like we say work done by a force in moving a ball from point A to point B. So ball here is your system and work is being done by an external force on the system. But in this chapter, we will always talk about work being done by the system. It could be negative or positive. So let us go ahead and discuss some special cases of the first law of thermodynamics. So the first one is the adiabatic process, and such a process is one where the entire system is so well insulated that no transfer of heat can happen in or out of the system. So we say that Q is equal to 0, and therefore we can write the equation as delta E internal is equal to minus W. So if the gas pushes the piston up, it does positive work, and let us for a moment take some number like 7 joules of positive work done by the gas. Then if you put W is equal to 7 joules in here, what we see is delta E is equal to minus 7 joules, which essentially means that the gas or the system has lost 7 joules of energy. And it makes perfect sense since the gas molecules are losing their energy while trying to push the piston up, and we know internal energy is nothing but the energy of all the molecules put together. So let us also see how this whole piece would look on a PV graph. So let us say you have the gas at some initial point P1 V1, and it is on an isotherm where the temperature is say 200 Kelvin, And we know that an isothermal graph has the same temperature on all points, or the product of P and V is constant on all points on this curve. So let's go ahead and make more such isothermal curves here. And so the temperature of this curve should be lower than that of this curve, since you can see for the same volume the pressure here is lower, and therefore the product PV will be smaller, hence the temperature will also be smaller. So this isotherm will be at an even lower temperature. Let's say it's 100 Kelvin. Now if you start removing grains of sand, what will happen is that the gas will expand, and since the system is insulated, the expansion will result in fall of temperature of the gas. So the gas will then come down to a new lower temperature and maybe fall on this new isotherm. And as you keep removing the grains of sand, the temperature of the gas keeps falling and it keeps plummeting down from one isotherm to another till it reaches this volume, which is P2V2, and this could fall on this isotherm, which I've already shown is 100 Kelvin, or it could have been some other isotherm. But if the piston pushes the gas down, then while the piston does positive work, we say that negative work is done by the gas. And let us say this time the piston does plus 8 joules of work, which basically means the gas or the system does minus 8 joules of work. Then delta E of the gas is plus 8 joules, or the internal energy of the gas has gone up. This again seems natural since the gas is being pushed by an external force, and in the process the molecules of the gas are getting more opportunity to bounce against the surface of this piston and increase the velocity and thereby the kinetic energy, and therefore increasing the internal energy of the gas. Well, another process we have is what we call the constant volume process. Now the second case is where we add heat to the system, but we do not allow the piston to move. The piston is in a way clamped and the volume does not change. So we say delta E is equal to Q, and I would again like you to visualize what is happening here. The heat is getting added to the system and the piston is not moving. There is no volume change, and therefore gas atoms are not wasting the energy in pushing the piston up, and so the gas does not do any work. So where will the heat go? It can only go towards increasing the kinetic energy of the atoms of the gas, and therefore the internal energy of the system goes up. Well, if we had the same situation, that is, we held the piston in one place, but let us say the heat reservoir was set at a temperature below the gas temperature, what would have happened was that the heat would have flowed out of the system and into the reservoir. Thus, the kinetic energy of the atoms of gas would have gone down, and so the internal energy of the gas would have also gone down. So the next process is a cyclical process where we can do whatever we wish to do with the gas, but in the end bring it back to its original state. Now, since the state of a gas on a PV graph indicates its internal energy too and is unique to that point, if we are bringing the gas back to its original state, we in a way restore the internal energy of the gas. So we can say that there is no change in the internal energy of the system, or 0 is equal to Q minus W, or Q is equal to W, or whatever energy is added to the system ends up in work done by the gas, so there is no increase in the internal energy of the gas. So let us say we take the gas from some value P1 V1 to some new value P2 V2, or it could be anything P3 V3, and you can see that there is net positive work done because there's volume expansion, and the work done is given by this area under the curve. And now if you take back the gas to P1 V1, you see you've reversed the process, and then the work done is negative because there's contraction. And if you sum up these two areas, one is positive and one is negative, what you get is this is the net area, which is the work done. And you can see since the positive value is more than the negative value, net positive work is done. So the internal energy of a gas does not depend on the history of what happened to the gas. You could have done anything with it, compressed it, heated it, or whatever. The internal energy of the gas at a point is just dependent on the position of it on this graph, that is its P and V coordinates. And well, it is quite obvious that all cyclical processes will always form a closed loop on a PV diagram. So the next process is free expansion, and this is a process in which there is no transfer of heat and there is no work done, or Q is equal to W is equal to 0. So the first law of thermodynamics then requires delta E is equal to 0. Well, it may be difficult for you to visualize under what situation can this happen. So here is a setup that can illustrate free expansion. What we have here is a gas which is initially confined to this part of the setup, and there is a closed stopcock here, and the other half is evacuated to create vacuum, and the whole system is then insulated. Now the stopcock is then opened and the gas expands freely and fills up both the chambers. What we see is that no heat is transferred since the system is insulated, and no work is done by the gas since it is expanding against vacuum and therefore does not have to do any work, or in other words, it has no resistance like piston or the atmosphere to work against. So an observation maybe some of you would have made is that a free expansion is quite different from other processes since it has not been done slowly or in a controlled way. As such, it kind of contradicts the condition we said in the beginning that the process needs to be slow to have equilibrium throughout the process. So in this process, we have indeed violated that condition, and at any instant during the expansion, the gas is not in thermal equilibrium and the pressure is also not uniform. So you see, we pay a price for this, and while we can plot the initial and the final state of the gas on a PV graph, we cannot plot what happens in between since all PV values are off the chart and not measurable for gas as a system. So that brings us to the close of this lesson, and one final thought I'd like you to take is that the principles of thermodynamics can be treated in a completely macroscopic way. That is, we do not need to worry about what is happening at a microscopic level or what are atoms and molecules doing and how they are interacting. In fact, that is what makes thermodynamics a very powerful concept, that it does not depend on how the matter is made at a microscopic level. So my question to you is, if you depressurize a can of compressed air and you feel the can cooling rapidly when you do so, what is the thermodynamic process happening? Leave your comments below and let us have a conversation. So if you like this video, go ahead and give it a thumbs up, and please do not forget to subscribe to this channel for many more interesting videos.